let me welcome everyone to today's IAS Distinguished Lecture, and we certainly have a distinguished lecturer today. And I wanted to begin with a slightly different perspective. Monday I was at the Chinese University of Hong Kong to give a lecture, and there's a place there, a very beautiful place, probably you have all seen, which has the title The Pavilion of Harmony. It's a very beautiful spot dedicated to a Chinese philosophical concept of the harmony between man and nature. And I can't think of any speaker whose science better illustrates that than David Milstein. And that is, chemistry and catalysis, we know, are very, very important to human life today. Really, not just a little bit, a lot. But it's very increasingly important that all of that catalysis and all that chemistry be done in harmony with nature, to not burn up resources that we'll never replace, not to create polluting byproducts, and to think in everything we do about that harmony. So it's a great pleasure to introduce David Milstein from the Whitesman Institute. I've known David for many years. Interesting history. His bachelor's was at the Hebrew University with a very famous catalytic chemist, Yochanan Blum. Postdoc with a guy who I think every organic chemist knows the name Stille. Postdoc with John Stille. And then he made a very interesting move to industry. And he was at DuPont Central Research for about 11 years, was it?
8, actually.
8, okay. Seems like 11. A very, very high-profile research organization, and he did very high-profile research. He then went back to his home country, Israel, and established, I think at the time he went back, there was almost no one doing organometallic chemistry. There was maybe 1 or 2 people doing a little bit of homogeneous catalysis, Spiro, for example. Mm-hmm. And he developed his work into a world center. And some of the themes of green chemistry, of course, are to not use platinum metals if we can, to use base metals, to use easily obtainable or sustainable feedstocks. And I think his research very elegantly highlights all of that. And because of that, he's been well recognized by all sorts of awards. And let me just give you some example. He's now the director for the Kimmel Center for Molecular Design. And he won the Israel Prize, which is Israel's highest scientific prize. I think that has $1 million honorarium, which is very nice. The ENI Award for the Protection of the Environment. ENI is the big Italian state chemical and petroleum company. The Gold Medal of the Israel Chemical Society. The European Prize for Organometallic Chemistry. And he's a member of the Israel Academy of Sciences, the German National Academy, the Leopoldina, a very old and distinguished society. And it's a little bit inaccurate because you won't become a member of the National Academy, U.S. National Academy of Sciences till you sign the book in April. But we'll let you off on that.
Okay.
You're close enough. So today he's going to talk about the design and applications of catalytic reactions for sustainable synthesis and energy. David, let's give him a welcome.
Thank you, Tobin, for this very generous and friendly introduction. It's nice to have good friends. So I also have another friend here, Istvan Horvat, which we know each other for many years, since the time he was at Exxon and I was at DuPont. And we go back many years. So I feel, so to speak, at home here. And thank you very much for the invitation for this distinguished lecture. And I hope you will not be disappointed. So let's just go. The title of my lecture is Design and Applications of Catalytic Reactions for Sustainable Synthesis and Energy. And for this, we are trying to develop new reactions that allow transformation that have not been known before. And if you look at the main goals of catalysis from my perspective, I can divide it into 3 sections. They are interrelated. So environmental benign and sustainable synthetic processes. I think it's one of the most important areas in chemistry. Energy-related sustainable catalysis. That's also a very important topic. Within that, there are several sections. So I just listed areas that we are involved in. So water splitting, hydrogen storage, advanced biofuel, CO2 conversion. I will touch upon the storage and advanced biofuel mostly. And then activation of inert, or so to speak, inert or less reactive molecules is an ongoing area. Still a lot to do in dinitrogen activation. Stoichiometric reactions of dinitrogen or very mildly catalytic are known, but still this is a far distance from the Haber process, so a lot to be done there. Also CO2 in synthesis, there's significant amount of work that has already been done, but much more to be decided. And regarding sustainability, there are many definitions of sustainability. The best one I found, the most that I like, comes from Istvan Horvat, which says resources, including energy, should be used at the rate at which they can be replaced naturally, and the generation of waste cannot be faster than the rate of their remediation. I think that's, for chemists or for scientists in general, that's the most relevant. There are other definitions that include politics, economy, and other areas, but this is the most relevant, I think, to my lecture. We're trying in our group to avoid this waste generation altogether. So both sustainable system and environmentally benign. Sustainable in terms of that they're using sustainable compounds like alcohols and so on. You will see. And talking about the needs of the pharmaceutical industry regarding green chemistry. So this describes this paper from about already almost 12 years ago, a meeting between major pharmaceutical players. It's AstraZeneca, GlaxoSmithKline, Merck, Pfizer, Eli Lilly, and Schering-Plough. Really big pharma. And they had this meeting to decide about which green areas are the most important for them. So they discussed, and then they had a brainstorm idea, and then they voted. This was a democratic process. And the result of the voting of this democratic process is shown here. So all 6 companies decided that amide formation, avoiding poor atom economy reagents, is highest priority. Then OH activation for nucleophilic substitution, for example, taking just alcohols without pre-derivatization and making carbon-carbon bonds and so on. And these are also important. Reduction of amides or hydrogenation without hydride reagents, no stoichiometric reductants, oxidation, epoxidation, and other ones. So keeping that in mind, we kind of designed some of the new catalytic reactions that were developed to address this type of issues. And the principle that guided us along this catalytic design is metal-ligand cooperation. So generally, catalysis is mostly, in homogeneous catalysis, is mostly metal-based. So the metal center of the complex is doing bond breaking and bond making. And the ligand, of course, has a major influence on the reactivity of the metal center, but by itself, it's not undergoing bond making and breaking. The idea of metal-ligand cooperation is that the molecule that it directs with the metal complex undergoes bond activation across the ligand and the metal. One fragment of the molecule resides on the ligand, and the other fragment resides on the metal. And this can go both for bond activation or bond breaking and also bond making. This is not a new concept. here is a review of what was known until 2015. A prevailing mode of bond activation is this one, where we have a metal amido that is going to a metal amine via cleavage of dihydrogen. So a proton goes to the nitrogen, the amide, the nitrogen amide, and a hydride goes to the metal center. And this can continue in catalytic cycles, and this is the principle actually that lies behind the Noyori chemistry, the Nobel Prize winner, when he has chiral systems, chiral ligands involved, and he can hydrogenate, for example, carbonyl compounds enantioselectively to the alcohols. So we want to develop new reactions, so we have to find a new metal-ligand cooperation mode. And the metal-ligand cooperation mode we've developed is based on pincer-type complexes, simple compounds which are tridentate, meridional, and they, if you remove a proton from this type of complex, you can get dearomatization. This is a dearomatized, so to speak, non-aromatic complex, which upon addition of various molecules, and you can see some listed here, and various metals, it's possible to now cleave the molecules. Part of it goes to this carbon, and part of it resides on the metal center. And the resonance energy of pyridine is lower significantly than that of benzene, so we don't sacrifice that much by going from aromatic to here. But the process is actually reversible in many cases. We can also make bonds going this way. You will note also that this amido metal bond is stronger than this just dative double bond. So the difference in energy is not high, and that's important for catalysis. We don't want in the catalytic cycle to have intermediates that are too stable. We want to complete cycles, and we don't want sinks in the catalytic cycle. And another feature which is interesting here is that there is no change in the metal oxidation state. Like Tobin mentioned, this allows quite readily to go to the first row metals, first row transition metals, because oftentimes the first row go by one electron processes, the second row goes by two electron processes. And if there's no change in oxidation state, at least overall, then this seems to be suitable also for the metals like iron, cobalt, nickel, and so on, as I will show. So with this in mind, we've made these complexes, and we wanted to see whether one can design catalytic cycles which were unknown before. So here is an example of an aromatic, dearomatized, so to speak, ruthenium complex. The dearomatization also has another feature. It generates an empty coordination site by removing a proton from here and a chloride from here. And it is stabilized somewhat also by the ylide form, as we can judge from the crystal structure. Now, the simplest thing is to see what it does with hydrogen. So with hydrogen, you can see aromatization takes place, and then you get this trans dihydride. So actually, a hydride goes to the ruthenium, and a proton goes to the side arm, and this is now an aromatic system. And this is reversible, like we expect it to be. A hydride picks up a proton from here and goes back here with the aromatization. Now another molecule can be activated, several others. Here I show just an alcohol. And you will see in the lecture that we use quite a bit of alcohols, and most alcohols are really come from sustainable resources. So protonation of this part and then alkoxide addition here gives this now coordinatively saturated metal complex. And now for people that took organometallic course, it's quite obvious that it's possible to connect these two and combine a catalytic cycle, provided that we're able to do beta hydrogen elimination. But the classical mechanism for beta hydrogen elimination requires an empty cis coordination site. So assuming that we can generate a complex with this, that the one arm will open up, a hydride can be abstracted, generating an intermediate aldehyde and this trans dihydride. And we already know that the trans dihydride is capable of elimination of hydrogen going to this. So this could be a catalytic cycle, provided we can have these elements, unsaturation, hemylability. And indeed, we can, we have, based on these simple concepts, we have prepared this complex. So you see it's non-aromatic. It has a strongly bound phosphorus atom and a weakly bound, relatively weakly amine arm, and we know that this arm is hemilabile. We've done NMR studies that confirm that. And this is now a catalyst that can catalyze conversion of alcohols to esters with liberation of hydrogen gas. And this reaction requires very little catalyst, just 0.1 mole%. It proceeds under neutral conditions, and it's driven by hydrogen liberation, effective hydrogen liberation. Even if it's uphill by a few kcals, efficient dihydrogen liberation drives it. And the mechanism of it overall involves an aldehyde intermediate that reacts with the alcohol to give a hemiacetal. This hemiacetal, being an alcohol by itself, liberates hydrogen and gives the ester. So it's a very simple process. Doesn't generate any waste unless you consider hydrogen waste, but hydrogen can have good use, and we could exclude the Tischenko type condensation of the aldehyde in this process. And just showing you one example, not from our group. So this catalyst has been commercialized several years ago already, and here, and some groups are using it. Here's one group that took diols and made esters with no waste whatsoever, taking diol and making hydrogen gas and polyesters. And interestingly, to drive this equilibrium of hydrogen liberation, they perform ester generation under vacuum. So that just mild vacuum will suffice, and they get respectable molecular weights. This is the group of Nick Robertson, and that is just one example of the use of this type of reaction. Now, this is actually, we call it acceptorless dehydrogenation. This is acceptorless, meaning you generate hydrogen gas. You don't need an acceptor to carry out the reaction over. And there is a review. This is a rapidly developing field, even since this year. There are now several acceptorless dehydrogenation systems. Now, if now you apply hydrogen pressure, you can run it the other way around. So with the same catalyst, you can hydrogenate esters. And hydrogenation of esters is an important industrial process. And when we did this work, actually industry was using 200 degrees and 200 atmospheres for hydrogenation of esters. So it's a very important process industrially. And with this catalyst, it's possible to carry it out at 5 atmospheres and 115 degrees under neutral conditions completely. Now we don't have time to talk about it, but if we replace one of the ethyl groups now with an H, we can have two modes of metal-ligand cooperation, both aromatization, dearomatization, amine, amide, and we can run this at room temperature. So the issue of ester hydrogenation is no longer a problematic issue. It goes very readily. And I should say there several other groups followed up this observation, and many of them use other type of pincer complexes. And one of prominent system is called, using this type of system that works by amidoamine, it can generate hydrogen. It's called the macho system, macho catalyst. Actually, it was commercialized by Takasago company for ester hydrogenation, but it does require 50 atmospheres and also fairly high temperature as compared with just 5 atmospheres. And as I said, we can do it also with some ligand modification at room temperature. Now, what else can be done with this reaction? Now, this is, I found it quite curious. Northland College is a school for undergraduates in Wisconsin. And you see how many names. Each one came for just a month or two and did some experiments. And these students had absolutely no experience in working with under inert atmosphere or handling complexes. Absolutely no experience. So they needed a little bit more pressure. And they took plastic bottles, cut them down. This is a picture from their paper. And converted them to diols, so waste plastic to diols. Also plastic that is based on polycarbonates, not only polyesters. So thinking further in terms of this concept of aldehyde intermediacy and using alcohol, we thought that we might be able to develop conversion of alcohols to carboxylic acids just using water and a base. You will see systems in which we use just water for oxidation. So this is a reaction where you take alcohol and the water and the base, stoichiometric base, and generate first a carboxylic acid salt, and then you can acidify and get the carboxylic acid, and it's driven by hydrogen liberation. If you don't use a base, you get one cycle, and it just stops. The reaction goes by first dihydrogen elimination to give an aldehyde, which adds water to give the gym diol, which liberates then hydrogen to give the carboxylic acid, and carboxylic acid is then trapped by the base. If you just take the complex, this is a modification of the first complex that I told you. This ring is also hemilabile, we know, because it rotates. We could show that. So you do the same reaction in absence of base. You get the carboxylate addition to the metal center, becoming aromatic, and that stops there. But if you add a base, it will continue. So this is another reaction, just trapping the aldehyde in this way. And you can use it by developing now a new synthesis of amino acids. So just taking amino alcohols, various lengths, with this pre-catalyst, it requires a base to deprotonate this proton and this chloride, remove HCl. You can get carboxylic, you can get amino acid salts with hydrogen liberation with no pre-protection or added oxidant or high efficiency, just using water and a base. Another reaction which I think now if you remember the priorities of the pharmaceutical companies, amide bond formation. So I think this reaction has, in my mind, quite a significant potential. So you can take now an alcohol, an amine, and make an amide with hydrogen liberation using this now commercially available catalyst. It requires only 0.1 mole%, neutral conditions, no waste, high yield, high turnover. And this is a new amide bond synthesis. So it can be selective. If we have both primary and secondary amine groups, the primary are more reactive, so you can do just the terminal one without touching the secondary amine. But it's possible to derivatize also the secondary amine under a little bit more forcing conditions. And several other groups now reported this type of reactivity, this type of reaction in various systems, many of them are pincer type, other derivatized. But this is still, in my view, it's still the state of the art in terms of neutral conditions, low catalyst, and high spectrum of reactivity with various compounds. Now, the reaction in our lab diverge in various directions. You can take an amino alcohol and in this case, which cyclizes to give the caprolactam. Caprolactam, of course, is a very important industrial chemical. If we just do it and heat it up, what we see in our bottle is nylon 6. So it gives this polymer. Polymers can be made also from diamines and diols, various functional polymers, polyamides. Polyamides are an important group of compounds. And you can also make peptides by using these beta-amino alcohols. And again, I like to bring examples from the literature just to show where it can go. Here is a paper from the group of Jibin Guan in California, where he took diols and diamines with various R spacers to get functional polyamides. And he obtained these polyamides, and since the reactivity of terminal amine groups is lower than internal ones, he could have in the chain secondary amine groups. So primary reacts further, and this type of polyamides that have an NH group in the chain turn out to be useful for gene delivery. So, and various other functionalities can be introduced. It's not our work, it's the work of Jibin Guan. The mechanism of this reaction, a simplified mechanism, involves first OH activation, like we've shown before, hemilabile arm opening, which then results in beta hydrogen elimination to give the trans dihydride. The trans dihydride liberates hydrogen, and then we have one cycle that generates this aldehyde, like we already mentioned. Now, this aldehyde reacts with the amine to give a hemiaminal. Now, hemiaminals, normally, they would liberate water to get an amine, but that doesn't happen here. The hemiaminal liberates now hydrogen. You get this addition of the hemiaminal to the complex, and it then abstracts a hydride from here, giving the trans dihydride and an amide. So this combination of the two cycles, it turns out to be quite efficient. And as I say, this is a simplified mechanism. And a case in point is shown here. If you just eliminate the hemilabile arm, then you get a completely different reaction. That is imine bond formation, not amide bond formation, just change in the structure, very similar compounds, but very different in terms of reactivity. And the explanation we give to that is that in order to go to make amides, the aldehyde has to be attacked while still coordinated to the metal center. And then by coordination, it reacts with the amine. The amine undergoes quaternization, and then there is proton transfer to the side arm. You get an amide with hydrogen gas. If there's no hemilabile or less hemilabile, the aldehyde falls into solution. And the aldehyde reacts with the amine in solution to give a hemiaminal that now is free in solution, and it liberates hydrogen to get an imine. Well, imine bond formation turns out to be also of synthetic value. Here's one example. So we all know that pyrols are very important organic compounds. They play a role in synthesis, in biological systems, and all that. So this pre-catalyst, again, we need a catalytic amount of base to remove HCl from chloride from here and a proton from here. Catalyzes the reaction of amino alcohols with secondary alcohols to make pyrols with various substituents that can be used. And the sequence of events is shown here. You first have dehydrogenation of the secondary alcohol, followed by condensation of the carbonyl group with the amine, giving it now an imine, and then another dehydrogenation to give an aldehyde. The base deprotonates this activated CH bond and closes the ring. Water elimination that gives the pyrrole. At the same time that we have studied it, reported it, also the group of Red Camp in Germany did iridium catalysis for this pyrrole generation. Another reaction which can be competitive with the well-known Wittig reaction is the one in which you take an alcohol and a sulfone, and you can get replace the OH group with a CH2 group from the sulfone. You can also get the hydrocarbon. So you can convert alcohols to olefins, one carbon extended with hydrogen liberation using this pre-catalyst. And that goes like you have deprotonation of the sulfone, which then reacts with the aldehyde that is formed by dehydrogenation of the alcohol, followed by intramolecular substitution of the sulfonate and getting the olefin. It's not limited to extension by one carbon, just one carbon. You can take this phenyl sulfone. This bond is stronger than this one. So you can now deliver various groups to the alcohol and get various olefins with hydrogen liberation. For people that are familiar with Julia reaction also uses sulfones, but it's a multi-step process, I think 3 stoichiometric steps to go to this direction with just with ketones or aldehydes. We can do it with alcohols in one step, with hydrogen liberation, and this a new olefin type synthesis. Now this table is just for the students here. My friend, the late Takao Ikaria, actually put this sequence in one of his papers. He called it challenge levels in catalytic hydrogenation of carbonyl compounds. So these are the easiest. And when we did the work, there was not even one example in which you can hydrogenate dialkyl carbonates or carbamates or even ureas. Urea is actually the most difficult And the reason for this is actually this carbon has fairly low positive charge that resides on this carbon. So we thought that could be an interesting target, not only because it has not been done before, but these compounds are available from CO2. So indeed, with this catalyst, the dearomatized one, we can hydrogenate dialkyl carbonate, dimethyl carbonate, to give 3 equivalents of methanol. You need 2 equivalents to make this from CO2. Carbamates also you need just 1 equivalent of methanol to make it. You can get double the amount of methanol. And even ureas undergo this type of transformation. And before that, actually, people used cyclic dialkyl carbonates as solvents for hydrogenation of other compounds. So it was surprising to us that it can go even just with 10 bars. And it can now provide a low-pressure 2-step conversion of CO2 to methanol. But another direction is based on carbamates, and it has to do with CO2 capture. So in coal-fired power plants, oftentimes they use amino alcohols to capture. That's one of the ways they do it, to sequester CO2. And they can take this beta-amino alcohol and just using cesium carbonate. And with CO2, it's possible to get the cyclic carbamate. And then what they do is heat it up. They release the CO2 into tanks, and then they generate CO2 cylinders or tanks under pressure. This is a way to get purified CO2 in cylinders. And then people can do it with various things in synthesis or so, or use CO2 under pressure to hydrogenate it. So we thought, since we can hydrogenate these carbamates, why go through release of that? Then you don't recover all of it, and then you do take the pressurized CO2. Why not hydrogenate this directly? And indeed, if you take this pre-catalyst, you just treat it with 10 atmospheres, you get quantitative conversion of the cyclic carbamate to methanol. No need for releasing the CO2 from it. You go directly to methanol in this sequence. Now, just very few examples of work that can use what's, so to speak, earth-abundant metals, first-row transition metals. So here's one example, a simple example. This is another pincer complex. It's the hydrobromide. With the catalytic amount of base, you can generate a dearomatized. So we take this pre-catalyst and catalytic base, and it can hydrogenate carbonyl compounds at room temperature just with 4 atmospheres hydrogen. So it's quite competitive with the chemistry of ruthenium. Room temperature, low pressure, hydrogenation of carbonyl compounds. And you can also take this boron derivative directly. And the mechanism is that we believe is operating. The active catalyst is this dearomatized. It's unsaturated. It can bind the ketone, followed by transfer of hydride to the carbonyl, giving this alkoxide. Now, hydrogen can react with this compound, with this dearomatized, as we know, as we've shown with ruthenium, giving now this hydrido alkoxide. And this alkoxide is like an internal base. It picks up a proton from the side arm, giving the alcohol and going back here. And this is not very stable, but we can run it in ethanol, so this reversibility allows maintaining a significant concentration of the aromatized complex. You would think that the first reaction that would take place is hydrogen addition, but we don't think so, because if we make separately the dihydride, it does not react readily with ketones. So we think it's an inner sphere type mechanism. Another example is low pressure hydrogenation of carbon dioxide to formate salts, in this case sodium formate. So we know about the various steps involved in it. If we take the trans dihydride, it can insert CO2 to give the formato complex, and then by influence of base, the sodium, the formate salt is generated, and hydrogen takes the place of the formate salts, and the dihydrogen ligand undergoes deprotonation to give hydride. Maybe I spoke a little bit too fast here, but if there are questions, I can deal with it. And so we have demonstrated these two steps. If you don't have a base, you just end up with this. You add a base, you can go back. Another reaction, let's say with another earth-abundant metal, is Spiro synthesis. We've described it with ruthenium. Now you can do it with diols using cobalt. It's a different type of reaction, also making pyroles. The active species is a cobalt-1 complex. If you use the cobalt dichloride, it is reduced in situ to the cobalt-1. So one chloride is replaced by a hydride, and then it generates a hydrogen atom. So that's what we believe. But that's the active catalyst in the presence of catalytic base. And you can get, you take the diol, it is converted to the dicarbonyl compounds, followed by hemiaminal formation on one side, hemiaminal formation on the other side, 2 water liberations, and you get the pyroles quite readily. Another example is hydrogenation of esters, now with cobalt. It's an interesting story. Apparently, it's not the carbonyl compound that undergoes hydrogenation. It's a carbon-carbon double bond. So the carbonyl compound actually is in equilibrium with the enolate. The enolate undergoes hydrogenation, and then it is followed by the aldehyde generation and the alkoxide. The aldehyde undergoes further hydrogenation. We know that because, we believe we know that because if you don't have alpha hydrogen, if you cannot generate this enolate, like in the case of benzoates or trifluoroacetates, then there's no reaction. So it goes by this way. This is a feature of the cobalt system. Another catalytic system that we found useful in recent years is this type. It's analogous to the macho that I described, but it has a larger ring here. So we know that this large chelate can dissociate the amido, and that plays a role in the catalysis when this amine part can dissociate and is a heavy labile. This is actually a new reaction, surprisingly, not known with noble metals, not known with first raw metals, just giving this unsaturated cyano, or you can call it substituted acrylates that are being used in various reactions, including could be used in polymerization. And this requires no base, and there's no hydrogenation of this double bond. It's an interesting reaction. So first, the amine compound liberates hydrogen, this proton and hydride, to give this amido complex. The amido complex then reacts with an alcohol to give the alkoxide. A proton goes now to this amido, And now it can generate an aldehyde from this. It can generate, because this is hemilabile, I didn't draw it, and it goes for this catalytic cycle for generating an aldehyde. Now, curiously, this amide complex is also quite basic. So it is capable of deprotonation of the nitrile, giving this type of complex, which we prepared separately. So it acts both dehydrogenation catalyst and also as a base, and then we get this olefinic cyano complex. We have several other examples with base metals, but I think this is just shows the principle. And okay, and now briefly into a story also of metal ligand cooperation, but with a different system. It has some interesting results. So this is with an acridine type of system. You will know that there is a CH2 group in both places here. It's a larger ring structure. If we treat it with a base and deuterium, we end up that one deuterium atom is bound to the ruthenium and another one to this position. This is C9. So deuterium adds across the metal center and C9, which looks like it's a remote position. But it's not really remote because, by the way, also with ammonia, if you treat it, you get dearomatization of this part, and the hydride is being pushed to this position. So if we look at the crystal structure of this compound, the distance between the nitrogen and ruthenium is almost 2.5 angstrom. It's 2.479. So this is a hemilabile. And once it detaches itself, hydride can go into this position. We can see it in this. This is based on DFT. So hydride direct transfer from the ruthenium center to position 9 of this acridine type ligand. This is supported by DFT. And several years ago, we actually more than 10 years ago, we've seen that this catalyst can catalyze formation of primary alcohols selectively to primary amines. Various amines are useful here. Actually, it was picked up now with by BASF company. They instead of isopropyl, they put cyclohexyl groups, and now it's completely selective with various systems to it. And primary amines, of course, are important intermediates, very important. And normally, the problem is that amine, the product primary amine, is more nucleophilic than ammonia itself. So you get mixtures of primary, secondary, tertiary. But because of the bulk here, ammonia has a preference. So this reaction goes very nice. But what I'm going to tell you has a different direction. So you can take, we've seen recently, well, not so recently, 5 years ago, that you can reverse this reaction by taking an amine and heating it up with water with the same catalyst. It liberates ammonia, which is, one can say, a useless reaction, but it sends a message. Nevertheless, one can use it, taking diamines and cyclizing them to cyclic amines. So if you convert one NH2 with an OH, this OH will be dehydrogenate to an aldehyde, and then it cyclizes and gets hydrogenated. But we wondered, how does this reaction go? So what we thought, and then we've proven also, that the sequence is dehydrogenation to give an imine, Now the imine adds water to give a hemiaminal. This hemiaminal liberates ammonia, the NH2 and the H here, to give an aldehyde. And then the dihydrogen that is generated in the first step hydrogenates the aldehyde to give the alcohol. If R has an NH2 group, then there is cyclization to give this cyclic amine after hydrogenation. But the question we asked ourselves, we know that with our amide bond formation, hemiaminals can undergo dehydrogenation rather than ammonia generation or water generation. So can we find conditions in which we can liberate hydrogen? This will mean that you can take a CH2 group and convert it to a carbonyl group using just water. And indeed, making a long story short, if you take cyclic amine and heat it with water at 130 degrees, hydrogen bubbles off the solution, and you get now the lactam. And this is just water. And people say, well, it is thermodynamically seems to be counterintuitive, but you have to efficiently remove hydrogen, and then there's no problem. You can just oxidize this CH2 group to a carbonyl group using water. Protons, of course, are the oxidants. And we're following on this, using water as an oxidant, thermal oxidant. And this, we've been able to isolate the cyclic amine. We've seen that it's capable to make this hemiaminal, and it is capable of dehydrogenation. The mechanism has been studied carefully, both experimentally and by calculations. Now, a few words that I'm going to say about advanced biofuel. And this has to do with the history of our country. So if we look at the energy density of alcohols, so methanol has the lowest energy density, ethanol higher significantly, but still much lower than gasoline. So as we go from ethanol to butanol, the energy density increases. And then with octanol, it's almost the same as gasoline. So there is a tendency now. A lot of work has been done. We were not very heavily involved, but we did some work here, in which instead trying to convert ethanol to longer alcohols. A lot of work, particularly to butanol, but octanol and hexanol have higher energy density. Ethanol has, in addition to having a lower energy density significantly than gasoline, it can also corrode engine and easily absorbs water. So we thought about having it convert in a very efficient way to longer alcohols. Now here is the history of our country. I come from the Whitesman Institute. It's named after our first president, Chaim Whitesman, which you can see is in his lab. He was a professor of chemistry at Manchester University, and I have his laboratories now in our building. I'm located in...
Smoking a cigarette here? Is that...
You know, the old-fashioned chemists, they were immune. With so much experience, no, they don't fear. They just go directly, yeah.
Burning a cigarette and making the fuel. See if it's flammable.
Actually, I give lectures in our country to high school students. At that time, I think, Tobin, I just cross out this. I don't think, I don't want to give them ideas of what to do in the lab in this way. But that's a real picture. And Tobin, did you go to the little museum that we have? Yeah, you've seen that. So, yeah, so he was our first president, really a visionary. established the Whitesman Institute in 1936, when before independence we were surrounded by many hostile countries, including inside the country, hostile population. And he said, we need a world-class institute. We have immediate needs, but I'm going to think a little bit long range and generate a generation of scientists. So why am I showing it? Whitesman developed a fermentation process to develop this, to generate the ABE. ABE is acetone, butanol, ethanol. The major component is butanol. If you change conditions, then you get only acetone. And acetone during First World War was critical for the war effort of Britain because it was used in the manufacture of cordite. Cordite is a smokeless gunpowder. And they were extracting acetone from wood, from trees. They were cutting forests just to extract acetone. And here comes this, at that time he's way younger than here, and it has this process using bacteria, Clostridium acetobutylicum. So acetobutylicum, so it made acetone and butanol, and he can make only acetone if he wants, that he actually isolated. It's a bacteria after his name. He isolated that by kind of with methods that are known were known at that time, selection, and it was industrial in 1916, and it's one of the processes, the AB, that are century old, that are still practiced, and you can see here's a map of China. This is the Corn Belt of China, so you can see first generation that was 1960, 1965. These are ABE fermentation industries. First generation, the red ones. Second generation, here you have several plants. Third generation, you have here, still functioning, making this ABE as a fuel additive. In various plants, I just show here the Chinese industry involved in that, but in many countries it's still functioning. Okay, so where do we come in? We have shown that we can take alcohols, dehydrogenate them to the aldehyde, and then with another molecule of amine or alcohol, we can convert them to the hemiaminal or hemiacetal. And then this will dehydrogenate to give the amide or the ester. Now we thought, since we have an amide, an aldehyde, if we use a base, we can cause condensation and end up with longer alcohols. This is the Gerbet process. It's a well-known process, actually also used industrially, but very inefficient compared to what can be done. So we thought we wanted to try it, so we took ethanol with this type of complex, acridine-based complex, and we can get a mixture of butanol, hexanol, and octanol. And we could reach quite high turnovers. I think it's a record, at least was a record at that time when we published, and with quite high conversion. And this is the combination of high turnover number and high conversion is quite unusual. So if we look, for example, so this is the selectivity to butanol. The selectivity goes down, and the yield of butanol goes up to a level and then stays pretty much constant because it is converted to the higher alcohols at the same rate at which it's generated. So there's no change no significant change in the yield of butanol over time. But then you get increase of the C6 and even C8. We stopped at a certain stage, but it can continue further. And this is, we could isolate this compound. This is the crystal structure. It's a dearomatized compound, so hydrate transfer goes into this position. And we have this cycle. In this case, we believe that an alkoxide is generated by virtue of proton transfer to this. So we get this alkoxide, and hydrogen is liberated, giving the alkoxide, followed by beta hydrogen elimination. And the bound aldehyde can undergo readily activation. If it falls in solution, it also undergoes condensation, but this is a more favored intermediate, we believe. And now another story of that I will finish quite quickly, but I think it's a significant story about hydrogen storage. I just going to give a little bit of background here. Hydrogen storage is actually a major challenge facing the hydrogen economy. It's described in this review, Accounts of Chemical Research by Professor Wasserschmidt. And if we talk about hydrogen economy, and we want to explain it to the public, so here's a picture that I picked up from the internet of a bus in Iceland. So here's the theory. Here's the water molecule that is drawn on the two doors of the bus. As the door, this is a double door, opens up, the water molecule is split. This is obvious to the observer. And then dihydrogen goes through a fuel cell. This fuel cell generates energy, generates electricity and water. So if you have water and you can split water, say with sunlight, it's a good source of dihydrogen and generating electricity. But using hydrogen directly is a problem because there are safety issues. Hydrogen has low energy density. One has to consider when we calculate the energy density by weight, also the weight of the storage container and energy spent for pressurizing or cryogenically generated. And there have been many approaches to get hydrogen storage. The idea is to have compounds which can have a considerable amount of hydrogen in them, and use, instead of using hydrogen, using them. Then they can liberate hydrogen and be regenerated. I won't go over all this, but all of them has their limitations, and the DOE target for 2020, it's not so far, is 5.5 weight percent, including weight of the system. This is a problem if you use the cylinders. So many groups are now involved in liquid organic hydrogen carriers. Not only now, the concept is very simple. You take an organic liquid. By virtue of a catalyst, you generate hydrogen, which generates another organic compound, which is now hydrogen depleted. And a condition then is that it should be able to be hydrogenated to this hydrogen-rich compound. This is the simple principle. When we studied this dehydrogenation was actually the limiting part and thermodynamically uphill. So here you can see, for example, using formic acid, so just formic acid generates hydrogen, and there's a fuel cell. It drives the car. But this is not really a good hydrogen storage system by virtue of then converting CO2 to form it. That's possible. But the hydrogen capacity is quite low. It's just about 4%. So, but it demonstrates the system. We've used here, has been used, we've used this iron catalyst. And well, it wants to keep running. And the requirements of liquid organic hydrogen carriers, you need to have high hydrogen capacity, easily store it, and release it relatively easily. And then the spent compound, you don't want it to be a gas. You want it to be another organic compound. And you can hydrogenate it. And ideally, you just use the gas station infrastructure. Here's just two famous examples. One, N-ethyl carbazole, air products. Very nice system, but that's uphill, endothermic. And quite a high temperature, 230, which cleave this nitrogen carbon bond. So the compound is decomposes with time. Nevertheless, they invented a lot of developments, and they ended up with this announcement: breakthrough for hydrogen fuel storage is like a liquid battery. So actually, this liquid generates electricity, right? Because it goes via fuel cell. So you just use, but the problem, the fact that at that temperature the compound was not stable, that was the main issue involved. They also need two different catalysts for both processes. Ideally, you would want to use just one. And a leading example is this dibenzyl toluene, which also suffers from the issue that quite high temperature is required, and it is endothermal. But nevertheless, it has a considerable exceeding the weight percent, the DOE target for 2020, 6.2 weight percent. And here they can go both ways, but stability is an issue here as well. So how can we contribute to that? And this is amide bond formation. We talked about amide bond formation, synthesis of amides, giving polyamides, giving peptides, and so on. So it's a new reaction, so one can do it also for this purpose. If you take amino ethanol, it's both an amine and an alcohol. It couples with itself and gives this cyclic dipeptide. And this is now exergonic. This is thermodynamically favorable. Not by very much, just 6 kcal, but considerable. It's one of the few examples where it's actually the dehydrogenation is thermodynamically favorable. And then you could also hydrogenate it back to the ethanolamine. Ethanolamine is very cheap. I think at the prices now it's just about double than gasoline, but it's not consumed. You're generating it. So this has 6.55 weight percent, inexpensive, the same catalyst for both directions. The conditions are fairly mild. And the price of ethanolamines, 15, that was long ago, 15 euro per kilogram. And the N-ethyl carbazole is more than 10 times as much. But we're still far from having a technology in hand. We're working on it. We need to lower catalyst loading to ppms, enhance long-term stability, and enhance selectivity because we get some also oligomers. It's not a major problem because everything hydrogenates back to ethanolamine. And so this is a direction, another direction that we have in our group. And in summary, we took alcohols. One can view alcohols as sustainable in the sense that they are available from biomass, they are available in various ways. So alcohols we can convert them to esters and hydrogen, and also to polyesters, including other groups that did that. The reaction can be reversed by using hydrogen pressure. Even mild pressure, just 5 atmospheres is enough. Then it's possible to use amines and make now amides with hydrogen. And this has led to polyamides, to peptides, and also I just mentioned hydrogen storage. And with reaction with amines, now if we have a different catalyst, in this case the one that doesn't have a hemi-label arm, we can get imines, and this has led to pyrazines, to pyroles, to pyridines, to quinolines. I didn't describe all of those, but all of them are available. Now reaction with ammonia can be selective to primary amines, and using water it's also possible to convert it back to the alcohols with liberation of ammonia. Using water in a base, one can get carboxylic acid salts, no oxidant added, no external oxidant, just water. With sulfones, it's possible to now extend the chain of the carbon chain with another carbon and generate olefins. It's a very easy reaction to do, just with sulfones and getting olefins. Hydrogenation of dialkyl carbonates is quite goes straightforward at 10 atmospheres. This is available from CO2. So in case of the dimethyl carbonate, you generate increase the amount of methanol, 3 equivalents, and it's possible to hydrogenate even the ultimate inert carbonyl compound, urea, to alcohol. And we mentioned conversion of captured CO2 directly to methanol via the carbamate. We can take cyclic amines and react them with water and get lactams and hydrogen liberation and superior biofuel. This is a side project in our group, but I thought I'll mention it here. And base metals have been used several now. And this is not my group right now. It's just people that over the years were involved in this project. My group is, I have about, I think, 12 people, mostly postdocs. And they are listed here alphabetically. So all of them, many of them are postdocs, very efficient postdocs, very excellent. Some of them come from China, and they have positions by the 1,000 talents in several universities. So I'm really indebted to my postdocs. They come from all over the world. And we collaborate with the DFT calculation, the group of Jan Martin. He's doing development of DFT methodology. And we can see other groups that we work with. And financial support comes from these agencies, including one from Europe, which is quite generous. And you can see one group trip that we had. The people stand here at the lowest point in the world. It's 400 meters below sea level, Mediterranean. This is the Dead Sea. It's quite large. We don't see it here from this perspective, but it's quite large. And this sand has therapeutic properties, even more so as you come closer to the water. So, and these people, some of them took advantage of it, particularly those that deal with energy. You can see. They liked it, and these are the one that deals with energy, obviously, in the group. And I thank you very much for your kind attention.
I assume you'll entertain questions? It's a beautiful lecture. Questions, comments? Yes.
You observe competitive dehydrogenations of amine besides the amide formation.
Competitive dehydrogenation to imine, for example, or to nitrile, converting an amine to triple bond or amine. Yeah, we can convert amines to imines. We can recently also convert amines to nitriles.
real question is, why is the amide formation so selective with the alcohol dehydrogenation preferentially occurring?
Yeah, well, because of the hemylability of the arm, the aldehyde stays coordinated long enough to be attacked by the amine. So when you get the hemiaminal, so to speak, it's in the coordination sphere. And so it's just you have hemiaminal that undergoes dehydrogenation. These systems are very good for dehydrogenation. So you generate an alcohol in the coordination sphere of the metal, and it just liberates hydrogen. If you don't have this free space, or it's not available long enough, for example, with the bisphosphine, then the aldehyde falls into solution, and then you get carbon-nitrogen double bond. You get an imine at that stage, so that's also possible. And recently we have seen also systems where you can get nitriles, which I didn't talk about it here.
Why is the alcohol dehydrogenation much faster than the amine dehydrogenation? Because the amine is more coordinating than the alcohol.
Actually, the amine coordination is not a desired reaction here. You want the amine coordination via the double bond, the lone pair on the nitrogen. At that stage, the NH is less accessible if it coordinates just via the lone pair to get the hydrogenation. So it's strong coordination, but it's not productive. In case of alcohol, the binding of the oxygen is much weaker. So you can get from the dative lone pair to get the OH available for activation. So that's a problem that we've seen also in other systems.
Another question, how hydridic is the ruthenium hydride and the manganese hydride? Do you have any idea about the range of the hydricity?
Yeah, we obviously the manganese hydride is more hydridic, significantly so, but it changes from complex to complex. So it has to have some hydricity, and you can modify the hydricity of the hydride by the other ligands that are coordinated to the metal. So there is a window of reactivity that it works. So with CO, it's fine. As soon as you put a nitrosyl, NO+ there, it's no longer hydridic enough.
Thank you. Other questions?
When you have the hydrogen bubble out, which is the driver, you're left with the catalyst and whatever you make. How you separate that efficiently to be sustainable?
How you separate the hydrogen from?
No. Hydrogen bubbles out. That's
Yeah.
easy. It
Okay.
drives your chemistry.
Yeah.
If you
So-
wouldn't have hydrogen, you would stop.
Yeah, we like
So-
hydrogen.
So
Yeah.
my question is, after you let the hydrogen go, how you separate your
How you-
homogeneous
how we-
catalyst with the solution?
How do we recover the catalyst?
Yeah. Or
So-
recycle, or
Yeah.
immobilize, or
Yeah. Actually, when we use 0.1% mole percent or below that, we don't bother doing it. For an industrial process, it would be an advantage to attach it covalently to a solid matrix, being it a polymer or being it a inorganic support to allow that. Normally for just organic synthesis purposes, since you use little catalyst, I'm not sure it worth the effort. But for hydrogen storage, that would be an important part.
There
So we,
comes the
so we,
killer question.
yeah.
What's the toxicity of your compound?
All students are alive.
Oh, I wasn't asking the student. I'm asking the compound.
This-
Because if you let the compound in your product, you have to be worried ends up in the wrong place. So
Yeah.
is there anyone doing any toxicity of the phosphine with the,
We don't know what BASF did,
okay.
and if they use it for, I don't know what's their end products. But we haven't done it. It's an important thing to do, particularly if you want to go into food type products or additives, certainly. But in general, I would say that iron is much less toxic than ruthenium. You can tolerate normally ppms of hydrogen, of ruthenium, but ppms of iron, but for ruthenium you can tolerate only ppbs. So from toxicity point of view, iron is much better. And we can do these things with iron. Actually, the amide 1 formation we published recently, we can do it also with manganese.
Just comment. This is beautiful.
So there was another question here, was that, yeah.
Just last Friday, another professor from California talking about taming methane here using the enzymes found in one species of the bacteria, just like the ABE reaction that you're talking about in the slide. I'm just would like to consult your professor expertise experience. Any kind of special metal-ligand complexes that so far you have studied have a very strong reactivity and reaction rate in terms of all these biomimetic and enzymatic reaction in converting the methane into methanol as well as other biofuels, so that in terms of the scaling up in the engineering processes that can be in favorite choices over other complexes. Thank you.
When you mention another professor, do you talk about Sunny Chen, my friend? Yeah. I can't compete with Sunny Chen with these copper systems, and we're not dealing with methane functionalization. That's of course a very important. But this biomimetic system that he has developed has, I think, real potential for methane functionalization. We didn't deal with actually hydrocarbon activation. There are many other groups that do it. I think we wanted to take it in different directions, so which end up with transformations that are currently in need of industry. And I mentioned, for example, pharmaceutical industry, also using water as an oxidant and so on. Methane, it's a very important thing, but in our department, Ronnie Newman can convert ethane to acetic acid, for example. That's a very important thing. But yeah.
Other questions?
I'm curious on the amine and polyamine process you showed. So is it kind of a natural process, or is it kind of a laboratory man-made process for that kind of quick reaction to happen?
On which transformation? Amine to?
Amine and
to polyamide?
And polyamide, yeah.
Polyamide, not polyamine.
Polyamide. So is it kind of a natural process, or is using this kind of catalyst a natural process, or is it a man-made control process?
I'm not familiar with a natural reaction or enzymatic reaction that can convert alcohols and amines to amides with hydrogen liberation. I don't view myself as an expert in enzymology, but I don't think this exists.
And another thing I would like to ask is that you're talking about long trains of hydrocarbonate. So how long actually can you make do they talk about the ABE? How long those kind of trains can become?
In our, I think we've been able to reach C8. You don't want too long. If you want it as to use it as a fuel or fuel additive, there's no real advantage to make it longer. It's already with C8. It's close to gasoline, very close. And as you make it longer, it becomes solids. There's no reason why it can, if you react it long enough, that the chain will not be increased. But I think the ultimate goal is C8 or C6, C8.
And how fast is those kind of conversion into those kind of C8 chains?
Conversion of ethanol to C8, for example.
Yeah.
It's not a fast process. The one that I showed, getting this mixture, we ran it to 40 hours.
So does your reaction become cold over time when you release hydrogen?
Does it become cold?
Yeah, is it endothermic? Can you feel it? I'm just curious.
Well, we didn't try to touch it. I think if it's cold, it's probably, well, the hydrogen release takes place only upon heating.
I'm heating. Hydrogenation, I remember, usually is exothermic.
Yeah, 25 kcals per mole, something like that, for hydrogenating a double bond, carbon-carbon double bond.
I'm just curious.
Yeah.
It's an entropy-driven process.
Yeah. So entropy, of course, generation of hydrogen is entropically favorable, so that drives the reaction. Yeah. But if you don't heat, you don't have hydrogen liberation, so the cooling effect, you won't see it.
I see what you mean. Yeah.
So I had a question. I know that probably we were up against, I'll ask a quick question. So you had these beautiful reactions where you're making polypeptides. So what happens if there's a methionine or cysteine in there? Are these catalysts sensitive to sulfur poisoning?
I must admit that we didn't pursue the scope of that. There are different issues. You want to make also mixed peptides in a certain order, right, and so on. It's a project that I'm thinking of pursuing. In general, sulfur compounds that we've used as other substrates.
Sulfone is not going to be a problem.
No, sulfone, yeah. I mean thiols and so on, yeah. They seem to slow down, but bind reversibly.
You can imagine, in fact, that a thiol easily giving off hydrogens.
Yeah,
disulfides.
Disulfides. We've tried to make thio acids or thio esters by liberation of hydrogen from the thiol. That didn't work well. But not because of the deactivation effect. It slows down. There is some deactivation, but we couldn't see any hydrogen liberation in that system.
I think Jacob has. It's not a question, it's a comment.
No, because we have a gift to present to you. Thanks for your wonderful lectures.
Hey, thank you very much. That will be a nice memory.